Go ahead. Yeah. Okay. Okay. Let me just. Good afternoon, everyone. My name is Den Ho Tong Minh from Israel. So today I'm happy to share with you my insights in the estimation of tropical forest vertical structure with the spaceborne LiDAR from GEDI and SAR Tomography from the P-band data. So let's explore the structure. So okay. Remote controls. So we have to go to next this one. Next one. Okay. So okay. And for the point. Okay. 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 Thank you. So for the context of this work, so basically that's everybody know already for very well about the biomass. That's upcoming biomass will give us a remarkable data set for the forest study. And also currently we have also the spaceborne LiDAR data from the NASA. So basically that GEDI mission, they also offer a spaceborne active data for study forest in vertical information. So with the SAR tomography, that's it will be the first time that we have the tomography data systematically from the space with the biomass SAR data. So basically, that's with both data, we are there is a possible to observe the same thing, but with a little bit different point of view, because with the GEDI LiDAR data, we have the just single point, that is spark measurements, and with the tomography, we have the two-dimensional continuously image. So if we put together to see how it can be complement together and how it's performance. So that is the idea of this work. So the main is just we try to understand, to investigate, to have a better idea about the performance or about the complement between the two data, the GEDI and the TomoSAR acquisition. So to understand about the vertical structure tropical forest. So the study area, so basically that during the biomass mission, during the phase for study the performance, for the algorithm retrieval, for example, we have two main campaigns. So basically we have more than two campaigns here, but these two campaigns, TomoSAR and PolInSAR, they dedicated to understand better the forest, which is very thick, which is very dense in the tropical climate. So basically that during the TomoSAR, we get a lot of knowledge over there. That is the first time we can see that with tomography, we can see something in the volume, something related to say quite well with the biomass. That is the main objective of the biomass. And then we have a little bit issue with the TomoSAR data is we don't have the low high forest over there. So that's why we want to change to the PolInSAR to have something complement for the full range of the biomass, for the full range of the height, and also the biomass mission is something related to global map. So that's why we need to go to another continental to understand how well it is. That's why we have to combine TomoSAR and PolInSAR into different continental. So for tomography processing, so basically that's I do very classic processing. So basically that you heard a lot about how to use in the tomography data, using the different polarization we combine together with the HV and VV we put together in a certain colorimetry, and then we try to decompose it in such a way that, for example, we synchronize in a big matrix, and then we decompose it in sum of chronicle products, and then we try to synthesize. That's one related to the crowd and volume contribution. So basically the idea is just mathematically just the single value decomposition, and then we try to keep the two highest value, and then we try to associate with the crowd and the volume identifying contribution. And then the idea to use in SKB, why we want to use this one, because from the SKB we can retrieve the crowd contribution, and from that one we can retrieve the optical bus from the sensor to the target on the ground, and then if we are able to retrieve the optical bus like this one, we can able to remove the disturbance motion, which related to the navigation of the aircraft motion, we cannot be possible to localize. And then also we are able to understand the terrain correction because basically if we use in the Alton path, we opted to pass from the sensor to target, we are able to understand where is the topography. So in that case, we are able to remove the topography in kind of the data processing, because basically that's what we want. We wanted the forest, and the forest is something related to about 5 meters until something like 50 meters or 60 meters, and the topography is much more flat than that one. So that's why we don't want to dealing with a very high range of the data. We just ran about something like minus 10 meters to about 60 meters. That's why if we're dealing with the preference with 0 meter at the ground, is a very good one to do for tomography. And then after to do fake calibration with the SKB using the fake with associated with the crowd contribution, we have the good data sets. We can do covariance, we can do the carbon spectrum or music, whatever it is, to do spectrum analysis, or we can do very classic techniques like if we resort the data. We have the between the data in the multi-baseline and also the data we observe which constitute with the data in a multi-layer and the multi-baseline data. Basically, that the two data, they form a certain kind of the Fourier transform. So if we take the Fourier transform, we can do something like the multi-baseline data. So basically, from multi-baseline data, we do the Fourier transform and we can get the multi-baseline data, multi-layer data, sorry. So basically that, if we had the tomography data, that's the kind of say just a multi-baseline data. The key idea is the multi-baseline data, and we use the Fourier transform, and we transform that data, basically just transform. So from the multi-baseline data to multi-layer data. So basically that's the key idea of tomography processing. So, and it's very classic until nowadays. For GEDI processing, so in GEDI processing, so basically that the data is not continuously, so they don't have the two-dimensional image. They have to bond by bond, and each bond is characterized by something like 25 meter diameter, and they have to measurement something like what we call the coverage power and the full power. And usually that's with the full power, they have the better energy to see the crowd. That's why usually the sensitivity of the full power is very good to see the crowd with the LiDAR data. And why people want to have the cover data, laser also, because they want to have the big coverage from the data measurement. So basically with the GEDI data, we have two measurement of full power and coverage power, and the full power is much more be better than the coverage power. And each sock, they usually characterized by 25 meters. So remember, each sock, they have a 25 meter, and a long track that we have separate something like 60 meter, and the cross track is something like 600 meter. So that is the GEDI measurement. GEDI measurement is interesting because why? Because at a single sock, we can see the vertical information, like the figure on your right. You can see that the axis on the left is the elevation. So basically that's the elevation you can have on the right. You can have something like the height with respect to the crowd. So basically you see the curves. The curve that is corresponding to the energy with respect to the when they do interactive with the target, with the forest. We see something like in the volume. Here it's a caps in one example that when the forest is about 30 meter top high. So we see that they do some interactive in the canopy, and then they go and the signal is going to a little bit decrease due to attenuation, and they have a little bit response in the crowd. So basically that they have the curve, they have the vertical information like this one, and in the GEDI data, they try to use this information in a certain kind of what they call the cumulative energy within the waveform. So basically they divide the cumulative energy by 100%. So if they localize the reference relative height with respect to the crowd as a function of the energy. So for example, if we're talking about the relative height 50%, it will be corresponding to the location with respect to the crowd at the 50% of cumulative energy within the waveform. So that is the idea of GEDI data processing. So basically, we don't processing anything with the GEDI data because the mission they provide already the data. So we just try to understand it's very well with data we should to extract to understand. Okay, so we put together two, and we focus on first we just try to understand a little bit detail for the spectrum of what data we have. So we focus on TomoSAR in South America and Africa in Africa. So basically that in South America we have the Parakou and Nuras, and the spectrum you see here, the spectrum of the canopy high is something very just usually in the 30 meter, a very low sample, very low measurement can be observed. Less than 20 meters. That is why we get a lot of knowledge in the TomoSAR, in the South American, but we have to move to another continent because we don't have the spectrum in low range high. So when we move to the Africa, we have a quite full spectrum of the high, so less than 20 meters, we have many measurements. So we put together, you see here, on the middle you see, if we see all the measurements with respect to the GEDI data, we see the spectrum like this one. But if we consider the good quality data, that's what we try to understand the performance of GEDI here. So when we're talking about the good data of GEDI, we're talking about the full data, the full power source, and also with the sensitivity, that is probability that they are able to penetrate to a certain tree cover in the forest less than greater than 98%. So if we consider the all measurement and the other one with good quality data, what will they can guess? So you see here is in the figure. So we already mentioned that with the GEDI data, they provide the relative heights with respect to the crowd, but it doesn't mean that it gives you the direct measurements of the canopy height. So basically, that just gives you a very 100% measurement, and what we do is we try to understand which kind of metric which should be related to the height. So and then in a certain case, in a certain study area, you have to carefully validate that one, because some kind of people using the 100% like the curve you see here. Like we have considered two scenarios with the relative high 100% and the other one with full power and sensitivity greater than 98%. And you see here, for example, if you have many measurements, so sometimes people crazy. Oh, we need a lot of data. But be careful. We have to worry about the quality rather than the quantity. So you see here, if we consider just the full power and the sensitivity greater than 98%, we can get a better performance with respect to the LiDAR data. So basically, with the GEDI data, if we carefully select the good data, we can get something like 5 meter performance with respect to the LiDAR airborne data, which we have to collect the same time which we do with the SAR data. So we put together with tomography. So basically here we join work with the group of Laurent. So Laurent and Jules just helped me to use in the covariant matrix with the carbon to do the estimation of the best for the crowd measurement and for the canopy measurement. So basically we put together the LiDAR data and the tomography data and LiDAR data and GEDI data. So basically that's compare with the tomography and GEDI for both crowd measurement and for crowd elevation, and for the canopy measurement, we can see that the crowd measurement is some kind they have a good performance. In all case with the crowd and with the canopy, that's the more tomography with the airborne scenario, or they have a better performance. Why? Because maybe they have a better sensitivity to the target. They have a better penetration to the crowd, so that's why they can better characterize to the forest. So But basically that when we compare to GEDI and tomography with the perfectly scenario of tomography with the airborne data, we can see that the tomography is kind of say outperformed with respect to GEDI data. That is about the performance which we understand very well. That is the tomography, and that is kind of be high, so that is very quantitative, very easy to quantify. The next one is we talking about the vertical profile. So basically on your left, you have the GEDI measurement, and the other one is about the tomography with the vertical profile like this one. And you see here to both data, they are very sensitive to the volume matrix, and we usually that we can capture some information from 10 to 40 meters, and usually that the peak of the tomography is usually consistently low with respect to the GEDI data. The next one, we focus on the reflectivity. So basically, we have the ground elevation, the canopy height, and the profile, and we try to understand the sensitivity here. So to understand what can they do correlate, so we try to normalize in certain way at the maximum of each single shock in the vertical is equal once, and we put together to see here, and we see that if we take the GEDI data about the layer about something like 30 to 35 meters, and we do correlation with the tomography at a function of height, and we see the figure on your bottom, and you can see here very good correlation at about 30 meters. So basically, that if we can see, if we are able to get some vertical information, we always can see that we can capture more or less the volume information like this one, and they're quite consistent. So we go to a little bit with the simulation with the biomass data. There's no need to discuss because a lot of presentation talking about that one. The main message is even going to the low resolution, we are able to survive and would answer very good performance with respect to the biomass simulation. So here is my summarize. So maybe a little bit out of time. So maybe class we have talked gratitude for the end now. So thank you for joining. Thank you a lot.
Any question? Yes. So you mentioned that the GEDI it doesn't have enough sensitivity or poor sensitivity, but did you address the geolocation accuracy of GEDI? Did you find that the GEDI can have geolocation errors? In Gabon, we found some horizontal shift between GEDI shots and Elvis shots, which you don't seem to have. Did you do anything to correct?
Yeah, you're right. That the GEDI mission, they provide the quality of data at a function of time. They improve a lot. So at the level 1, we got a lot of problem with the geolocation errors, and sometimes the data is a little difficult to appreciate, but they improve a lot with the level 2 now. So the data we have is level 2. So they improve a lot.
I see.
So for the geology errors, I think level 2 is good, good enough to do comparison.
Thanks.
Okay, thank you for your talk. And in your slide 10, you compared GEDI profile with TomoSAR profile. And different polarization, yes, it's on. I'm wondering why even for HH polarization, the relationship between TomoSAR profile with GEDI looks still very high, because for this polarization, maybe there's more backscattering from the ground, but why for the
So why the correlation with the SAR with respect to tomography is a little bit low for around the ground? So that is your question, right? If I understand correctly?
No, actually, if you look on the picture, for the HH polarization, there's still some linear relationship between GEDI and TomoSAR.
Here we try to understand the linear relationship between the two data. So basically that they're not correctly the same units, but we try to normalize in such a way, vary from 0 to 1 and the maximum which relate to 1. So that's why we are able to see if there is any relative reflectivity. Do they have some correlation or not? And we try to put together to see here, and when we put together and we see very clear the phenomena that comes quite linear between the GEDI and tomography, but a little bit shift. So if we take the LiDAR data from 30 to 35 meters, and we do correlation like the figure you see in the bottom here, and we see the correlation which related to tomography is something related to around 5 meters. So basically, why? Because the tomography, they have the volume bit or the phase center basically consistent lower than the LiDAR data. Some kind of the 2 or 4 meters depend on polarization and depend on the height.
Okay, thank you very much.
Thank you.
How do you interpret this correlation? The one are 70 centimeters side looking and the other one is nanometers nadir looking. Why do you expect that they correlate?
So basically that we try to do we try to do G-coding to be sure that two measurements should be the same point of view. Basically, we try to G-code in the slant range data of radar data to the vertical with respect to the nadir look like the radar data. So basically, we try to match it perfectly before to do some analysis like this one. But of course, we have to very carefully for the pre-processing step to be sure that everything should be matched together before to do correlate, before to do comparison or to understand subsequent analysis later.
I don't speak about correlation. I speak just why you expect that a 70 centimeters reflectivity should correlate with a nanometer reflectivity at this height.
No, we don't expect that one. We just try to understand, put together to see if there anything to capture the volume volume information or not. We don't expect. At the beginning of this work, we don't expect anything. We just try, okay, here is the data we have, the GEDI data available, we have the tomography available. We just put together to see if there anything we can learn something about that one. And then not really we expect this one, but we see something like this one. Thank you.
Maybe, just to be clear, what do you exactly correlate here? Because for tomography, you have radiometry, so it's a number that tells you how much power is in that voxel. For GEDI, you have a point density, I think. So you correlate radiometry with the point density. Is that it?
So yeah, that's the right point. So basically that we try to normalize in such a way that the very units is from 0 to 1. So basically that with the GEDI data, like at the beginning, you see the GEDI profile, we have something like this one. So they we have something like this one. The volumetric, the vertical information that we vary from 0 to 1. We normalize this one, and we try to normalize the tomography from 0 to 1, and we put together like this one to see the linear correlation if they have, and we see something like this one.
So it's already a miracle
yeah.
that they match.
Thank you.
Okay, so thank you very much, Dave.
Thank you.